Hello, welcome. This is about a lab that is modeling the Newton's first and second laws with ordinary objects, and this is done using applications such as GlowScript and Tracker, and is done to represent how objects moving in vectors can be represented, and also how different forces act upon an object. The objectives of the lab are to model 2D motion on a plane with recorded objects, to demonstrate Newton's first law, as well as second law in terms of equations, investigate whether additional forces are acting upon a given object, such as normal force or other contact forces, and documenting the motion of bodies through an application such as Tracker Online. Lastly, it is also to corroborate relationships between velocity and position at a given time. The central principles or formulas of interest during the lab were Newton's first and second laws, meaning if an object is at rest, if there's no force acting upon the object will remain at rest. And similarly, if the object is at a constant velocity and there's no force acting upon the object, or the net force is zero, then there will be no change in the velocity. Second, momentum represents the mass of the object multiplied by the velocity of the object, which will remain constant for the purposes of this experiment, as the object does not change velocity and remains the same in mass. The object can be represented using vectors, such as the position of the object, as well as the velocity, and the beginning location for this plane of interest that we have chosen is 0, 0, 0. 0 unit vectors from the beginning in x, y, and z dimensions. And movement will be in the x direction for the purpose of the beginning of the experiment, and y hat is negligible in this system. The position update formula is also used throughout the experiment to indicate whether the object has moved a certain distance, and as indicated, since force net is 0, there will be no change in the velocity, meaning the final position in the x dimension will equal the initial position in the x dimension plus the velocity in the x dimension times the time. Lastly, iteration was also used for the purposes of the experiment in small time intervals of 0.033 seconds, and it includes a summation of all the possible intervals of time and the difference of position between the different intervals of time as a sum. This includes the video that our group had taken for the purpose of the experiment and is represented as a constant rolling object. We used small time intervals such as this to record the object and placed it in the Tracker application. In this video, we see the movement of the object as represented by the blue point-in-time indicators, and you can see that although the y velocity or the y position varies at many points during this experiment, the x position remains constant and increasing. But since the position in the y direction is negligible, we can assume that there is a relatively constant velocity of mass b, neglecting friction. Here we have the same video, but represented in vectors, so you can see how the change in direction indicates movement to the right, and the change in position is also from right to left, as the final position is at 0.5 and the initial position is at 0, meaning the change in position is 0.5. And velocity can also be represented in the right direction as the object is moving to the right along the positive x-axis. Finally, we have our results, and we take that and we put that in the GlowScript application to see what the predicted results are based on the initial velocity that we gathered from tracker. As you can see, we've also represented the program in GlowScript with a delta t of 0.033, which is the same as what we used in the tracker. The initial velocity in this case is 0.16 meters per second, as indicated in balled up velocity, and the initial position is at 0, 0, 0. We can also apply the momentum principle to update velocity and position, as seen here, as initial velocity plus force net over m times delta t, and initial position equals, or final position equals initial position times velocity times delta t. And this is how we can represent it visually. We can move to the video. And as you can see, the ball is moving at a constant velocity from the initial position. And although it's taking place over a period of 6 seconds, the time has been dilated to 0.5, so it can be better represented in the model. Additionally, you can see the position versus time, which is a constant increase from bottom to top and left to right, meaning the velocity should also be constant, which in this case it is, 0.16 meters per second. Here we can represent the values in a table of values, and this includes the time that was taken, the predicted position, and the actual position. And this is a small snippet of what we actually took from the actual values. Utilizing Google Sheets or Microsoft Excel is the primary tool that we use for this app. We can represent the position in meters and make sure everything is divided into equal intervals of time. And then we converted every position in meters into vector form to better represent the direction that it was moving. This is what we received when we looked at the movements on the x-axis. So as position increases, as time increases, so does position, and you can see it occurs at a fairly constant rate. And the actual position maintained a fairly steady regression to the predicted position done by GlowScript. The model can also be represented as a shifted model on the y-axis as opposed to the x-axis. Although the x-axis was our choice for the experiment, the y-axis can also be used to represent the orientation of the object. As you can see here, the object moves at the same velocity in the positive y direction, and you'll get the same results. As you can see, it's the same distance, same magnitude between the initial velocity is the same as the original velocity, just in a different direction, represented on the y-axis. A formula accordingly, including the initial position of the object in the y direction, and the final position in the y direction, and the velocity in the y direction. And the last section is also negligible because force net is 0. And this can be iterated again, this time including the velocity in the y direction, and it can be included as a summation of the total values. There are also contact forces on the object that we have to consider. In this case, gravity and normal forces are considered contact forces, as well as frictional force, which in this case equals 0. But we can better represent the total force as the force of gravity in the negative direction opposed by the normal force in the positive direction, which is, of course, going to equal 0. In the x direction, the force of friction is counteracted by the momentum, which means there is no friction in the system. And this can be represented as a free body diagram here. As you see, there are forces on all 4 axes, but as a whole, each force has the same magnitude and therefore equals 0. And again, in addition to this, there may even be more forces on the object that we cannot ascertain. However, they will oppose each other and equal 0 in this case, because we know for a fact that net force is still 0. As a summary, moving objects can be represented as vectors on a plane using interactive objects and written numerically in the form of Newton's laws of motion. Using GlowScript may assist in comparing the actual motion of the object versus its predicted model under constant velocity and acceleration. which is an important tool to indicate if there is net force acting upon the object. Forces may be further considered and calculated even if the net force is zero, meaning there are other forces that can still exist. And axes may be shifted in motion diagrams as long as magnitude remains the same, meaning that we can represent it in any plane, the negative y-hat direction, the z-hat direction, as long as we pick a plane and it remains constant throughout the entire experiment. Thank you. A short summary of the lab is that we determined that moving objects can be represented as vectors on a plane using interactive objects, and can be written numerically in the form of Newton's laws of motion, and can be described. Using GlowScript as an application may assist in comparing the actual movement of an object versus its predicted model under constant velocity and acceleration. Forces may be further considered and calculated even if the net force is zero, meaning there are other forces that can be part of the system that are just not represented because they cancel out. And axes may be shifted in motion diagrams as long as magnitude remains the same, as long as the people interpreting your results understand that there's been an axis shift, and all vectors can be represented accordingly and adjusted. Thank you so much for watching, and I'll see you next time.